Good morning. Let's continue our lesson. We're now on example 1.7. This is under the topic on complements, r's complement and r minus 1's complement. So example 1.7. Given the two binary numbers x equals 10101000 and y is equal to 10000011. These are both in binary. Perform the subtraction x minus y and y minus x by using 2's complement. So we are in the binary system and we are given the task to subtract this binary number x or subtract this binary number y from binary number x and vice versa using 2's complement. Recall what this 2's complement mean. How do we evaluate the 2's complement? 2's complement in general form is equivalent to the r minus, no, it's not the diminished radix complement but the r's complement. So we need to evaluate r's complement in binary, which is the 2's complement. To do that, we need to follow the steps. We have the step subtraction with complements. It's a very long process. We can just internalize it through an example. We already have this example 1.5. Let's go directly here. Just look at the example how he solved. So x minus y, write down our x, which is 10101000, and then the 2's complement of y. To find the 2's complement of y, we need to invert every bit and then add 1 to the last bit. Let's write it down. Oops. Wait. But we have y is equal to 1 and then 4 zeros. 1, 1, 2, 3, 4, and then 1, 1. 2's complement of this is, so we need to invert every bit, and then add 1. That is the 2's complement of y. So we add 1, 0 plus 1, 1, and then copy the rest of the bits. So this is the 2's complement of y. So x, what was x? X minus y equals, x is 1010, 1010, and then 100. Just add x with the 2's complement of y. So x plus 0, 1, 1, 1, 1, 0, 1. There's 1, 0. 0 plus 1, 1. 0 plus 0, 0. 1 plus 1. This is 2. And 2 in binary is 0, 1. So carry 1, 2. 2 in binary. Carry 1. So 1, 2, 3. So 3. 3 in binary is 1, 1. This is 2, so 0, 1. 1 plus 1, 2, which is 1, 0. So we have this result. We add x and the 2's complement of y. We obtain this result. So let's check if we have the same answer. Yes, 1, 0, 0, and then 1, and 3 zeros, and then 1. So the same result. And then it says here, discard and carry to the 7. The original digits are 1, 2, 3, 4, 5, 6, 7, 7. 1, 2, 3, 4, 5, 6, 7. We have the 7 digits, binary digits, and we have 1 extra bit from the result of addition of the x and the 2's complement of y. To discard the and carry 2 to the 7. Why did it say 2 to the 7? But if we write the exponents, equivalent exponents for each of these digits, the exponent here is 0. This is 1, 2, 3, 4, 5, 6. And the exponent of this one is 7. So, to discard this bit, it is equivalent to 1 times 2 to the 7. I don't know. Yeah. If we are to convert it to decimal. What we just need is to discard this bit. So we subtract 1, 2, 3, 4, 5, 6. Subtract this to the end, carry. So what will be left is 0, 0, 1, 0, 0, 0, 1. So the answer, the final answer, is this. X minus y is 0, 0, 1, 0, 0, 0, 1, or we discard the 2 bits since it's both 0, 0, so the answer is 1, 0, 0, 0, 1. What is the equivalent of this in decimal? If we convert this into decimal, the equivalent is try to convert that in decimal. It's easier with a calculator. Without a calculator, 0, 1, so 0. This is 1 plus, but this is 1 times 2 to the 0 plus 1 times 0, 1, 2, 3, 4, 2 to the 4. So 1 plus 16. So this is 17. Base 10. Anyway, we just converted and showed that this is the equivalent, decimal equivalent. It's not required. The answer is 1, 0, 0, 0, 1 base 2. Next is y minus x is 1, 0, 0, 0, 1, 0, 0, 0, 0, 4 zeros and then 1, 1, minus x. What is x? It's 1, 0, 1, 0, 100. I mean 1 0 1 0 100. This is x. This is y, this is x, but can you observe? What can you observe? Wait, but before going that, let's explain what we did with x minus y. Which is greater, y or x? 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. Both of them are 7 bits, contain 7 bits, and they start with 1. Then next is 0 0 and then 0. Here we have 1. So clearly we can see that x is greater than y. X is greater than y. So recall here r to the n minus n is the radix 2's complement. When we are in binary, r to the n minus n is the 2's complement. This is the 2's complement. So what we did, if we add Rm is x here, Rm is x, and then y is the 2's complement. And y is, instead of n, Ry is n. So we get the 2's complement of y, which is r to the n minus n. This r to the n minus y. This is the 2's complement of y. So if we add y, our x, if we add x with the 2's complement of y, which is r to the n minus y, the result is x plus r to the n minus y. X plus r to the n minus y, this is equivalent to this number here. This is x and the 2's complement. So x plus r to the n minus y is this. To get x minus y, we need to remove r to the n. That's why we subtracted r to the n, 2 to the 7. Rn is the number of bits, which is equal to 7. So 2 to the 7, and convert that to binary. This is 1 and then followed by 6 zeros. That's why we subtracted 1 0 0 0 0 0 0 from the result, so that the final answer is this 1 0 0 0 1, which is equal to 17 in decimal. That is for x minus y, where x is greater than y. Let's do the second one, which is y minus x. Ry is one followed by 4 zeros and then 1 1. Then 1 1 minus Rx is 1 0 1 0 and then 1 0 0. So the condition here is y is less than x. Y is less than x. What are we gonna do? Still the result y minus x, this is equal to y minus r to the n minus x. This is the 2's complement of x. If we use the 2's complement of x, so with the result, this is y plus x minus r to the n. Wait. Negative to 2's complement. Sum does not produce an and carry and is equal to, yeah, as what I have observed. This becomes y minus r to the n. He wrote it this way. If m is less than n, so if y is less than x, let's look at this. This is y and x. So if we subtract y, or subtract x from y, we know that the result is negative. So the form will be r to the n minus, it says here, r to the n minus n minus m. Rn is y, Rn is x. It's x r to the n minus m. Right? Still m plus r to the n minus m. Wait. It's kind of confusing. Let's just erase this one. Let's go back here. If y is less than x, so we will still use y plus the 2's complement. We will still use this, the addition of y, or the first number, or the minuend, plus the 2's complement of the subtrahend, so y plus r to the n minus x. We will still use this form, but we know that the result of this will not produce an end carry, so it rearranged becomes r to the n minus just confusing. Y less than x. Wait. Okay, so you'll rearrange this. It will become r to the n minus x minus y. So this will be the result if we add y with the 2's complement of x with this equal to y, and this subtract this x. So we add y to the 2's complement of x, where y is less than x, and what we want to obtain is y minus x. The result of this is y plus r to the n minus x, or we are rearranging, we get r to the n minus x. Then we put y inside the parentheses, so it becomes negative y. If we distribute the sign, negative times negative is still positive y. So this will be the result, but what we want to obtain is y minus x. It's letter B. Negative. There is no end carry, therefore the answer is y minus x is the 2's complement. If we look at this, the result, this is the 2's complement, right? But the form of the 2's complement is r to the n minus, if n is the number, the 2's complement of n is r to the n minus n. Therefore, our number here is x minus y. And the result that we obtained in adding y with the 2's complement of x is the 2's complement of x minus y. 2's complement of x minus y. So we add a negative sign. There's no end carries, so what we actually obtained is x minus y so we just added a negative sign. Okay. Therefore, what is the result? So y is 1 0 0 0 0 1 1 plus the 2's complement of x. The 2's complement of 1 0 1 0 1 0 0 invert every bit, then add 1 plus 1 2, which is 1 0 1 0, then 1 0 1. So 0 0 1 1 0 1. One, 1 0 1 1. Right, so this is x minus y. To get y minus x, we add a negative sign. So negative negative of the 2's complement. So it's still not yet the final answer. This is 2's complement of x minus y. So we need to invert this again. Negative 2's complement. 110, 1111. So invert every bit, so negative of 001, 000, 0 plus 1. So this is equal to the negative 001, 00, 01. This is the final answer. Negative 0010. Negative 0010, 001. It's kind of confusing at first, but you only need to practice solving, and then sometimes check it with a calculator if you have one. Let's go to signed binary numbers. Both signed and unsigned binary numbers consist of a string of bits when represented in a computer. The user determines whether the number is signed or unsigned. If the binary number is signed, then the leftmost bit represents the sign and the rest of the bits represent the number. So it depends on the interpretation or what was set by the user, whether it was declared as signed or unsigned. For example, we have 01001 and 11001. We can interpret both of these binary numbers differently depending on how we declared them, whether signed or unsigned. If we declared them as unsigned binary numbers, then the 0 here, the first bit, represents a normal bit, which is 0. So as the one here represents a binary digit 1. If we declare them as signed numbers, the 0 here means that 1001 is a positive binary number, while the one here in 11001 represents a negative sign for the binary number 1001. This is for the signed magnitude convention. When arithmetic operations are implemented in a computer, it is more convenient to use a different system, referred to as the signed complement system, for representing negative numbers. Signed complement instead of the signed magnitude. In this system, a negative number is indicated by its complement, whereas the signed magnitude system negates a number by changing its sign. The signed complement system negates a number by taking its complement. So for the signed complement system, instead of using 0 as positive and 1 as negative to indicate the sign, complements are used. See an example. Positive 9 in binary with 8 bits is 4 zeros and then 1001. Negative 9 represented with 8 bits for the different systems depends on the system that we are using. For signed magnitude, for signed magnitude, 2, 3, 4. The fourth or the leftmost bit is the sign for the sign magnitude. So -9, we just make the 0 here as 1 to indicate the sign. For signed one's complement, what happened? What happened for the signed one's complement? We just invert every bit. So we just took the ones complement of the number. And to get the ones complement of the number, we invert each bit. So this becomes 1 1 1 1 1 1 1 1 and then 0 1 1 0. So 1 1 1 1 0 1 1 0. This is the ones complement of this binary number. And that is the signed ones complement representation. That's how we represent -9. That's how we represent -9 using the signed ones complement. Using the signed 2's complement, so we take the 2's complement of this number, and that is by taking the 1's complement of this number and adding 1 to the least significant bit. So we just add 1 to the 1's complement. Add 1 here. So it becomes 1 1 1 1 0 1 1 1. This is -9 if we are using the signed 2's complement. Let's check this table 1.3 for examples. For the signed magnitude, it's easy. From 0 to 7, we just copy. 0 is the least significant bit to indicate that it is a positive number. Then the 1 on the least significant, in the leftmost bit represents that the number is negative. For the signed one's complement, it's the same as the signed magnitude. Everything is the same if the number is positive. It's the same for signed 2's complement, signed 1's complement, and signed magnitude if the sign is positive. But for the negative number, zero, there is positive 0 and negative 0. For signed 1's complement, positive 0 is just 4 zeros. But for the negative 0, it becomes, we take the 1's complement of 0 0 0, so it becomes 1 1 1 1. For negative 1, we invert every bit of 1, positive 1, so it becomes 1 1 1 0 1 1 0. For positive 2, if we want to get negative 2 using signed 1's complement, we invert every bit, so it's 1 1 1 1 0 1. That's why negative 2 here is 1 1 0 1, and so on. For the signed 2's complement, for example, negative 4, so we need to get the 2's complement of positive 4. To get that, we invert each bit, so it's 0 1, it's 1 0 1 1 plus 1, positive 4, positive 4. base 10 equals 0, 1, 0, 0 base 2. So negative 4 using 2's sine complement. So we take the 1's complement, that's 1, 0, 1, 1. 1's complement is just the invert of each bit. So 1, 0, 1, 1 base 2. But you add 1 to get the 2's complement. So add 1. So 1, 0, 1, 1 plus 1. 1, 1, that's 2. That's 1, 0. 2, 1, 0. 1, 1. So 1, 1, 0, 0 base 2. This is negative 2. Base 10. And negative 4 base 10. 1, 1, 0, 0. So negative 4 base 10 is equal to 1, 1, 0, 0 base 2 using sine 2's complement. Arithmetic addition. The addition of two sine binary numbers with negative numbers represented in sine 2's complement form is obtained from the addition of the two numbers including their sign bits. A carry out of the sign bit position is discarded. So if we add two sine binary numbers with negative numbers, we just take the sine 2's complement. For example, positive 25 plus negative 37. That is negative 37 minus 25, so equals negative 12. And in binary, that would be 6 in binary is 110. Positive 13 in binary is 1101. You should know this. 13 is 1101. I hope by now you already memorized or you already know how to convert 13 decimal base 10 13 decimal to binary. We know that 1000 is 8. Then 1001 is 9. 1010 is 10. 1011 is 11. 1100 is 12. 1101 is 13. Is 13. So positive 6 plus positive 13 is positive 19. We just add. But if we have negative 6 plus 13, that's positive 7. In binary, that is performed by using the 2's complement, sine 2's complement. Negative 6. We get the 2's complement of positive 6, so we invert each bit and add 1. Invert the positive 6. 1, 2, 3, 4. Right. 1's complement. 1's complement is 1, 1, 1, 1, 1, 0, 0, 1. Then we add 1, becomes the 2's complement. 0, get a 1. Then 0, 1, 1, 1, 1, 1. 1, 1, 0, 0 is 1. 1, 1, 1, 1, 1, 1, 1. 1, 1, 0, 0 is 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 1. 1, 1, 0, So 1111 1010 that's negative 6. So negative 6 plus 13, the answer is what did he do here? If we add both, that's 1 1 1 0 get a 1 0 get a 1. Let's look carefully. Let's add this two. So 0 plus 1, that's 1. 1 plus 0, 1. 0 plus 1, 1. Then 1 plus 1, that's 2, which is 1 0. So 0 carry 1. 1 plus 1, the carry. So 2. 0 carry 1, and so on. And then we have, actually we have a carry here of 1. That's 1 1 2 3 4 5 1 2 3 4 5, then 1 1 1. We just discard this one and take same as what we did. Same as the subtraction that we performed in example 1.7. Except that we emphasized that the equivalent of negative 6 is the 2's complement. Is the 2's complement of positive 6, and we just discarded the end carry. So please check these other examples. So this is very beneficial using 2's complement to perform addition and subtraction. Computers need only one common hardware circuit to handle both types of arithmetic with the help of the complements of binary numbers. BCD, or the binary coded decimal, these are the binary codes. One example is the BCD, or the binary coded decimal. Let's check the table. So what can you observe? For example, 185 base 10. In BCD, or binary coded decimal, it's just 001 1000 0101 BCD. It's just kinuha niya lang yung equivalent. It just get the binary equivalent of each digit, decimal digit. So we know that the binary equivalent of 5 is 0101. For 8, it's 1000. For 1, it's 001. So each decimal digit is converted to binary, and we'll take the binary equivalent of each digit. That's for BCD. If we take the binary equivalent of 185 base 10, that's 1010 1001. So check or see the difference between BCD and binary. They're very different. Let's look at other decimal codes. BCD 8421. BCD 8421. Each digit is represented by this equivalent binary bits. So it's the same for binary, but it's the same for binary for each digit, but if we have more decimal digits like 185, the the code will be different. So this BCD digit equivalence that we have represented here upstairs in table 1.4 is the same as the BCD 8421. That's the common. We also have other codes like the 2421. What's the difference with this? 2421. 1 is same, 2, 3 is same, but 4 is the same, but for 5 it becomes 1011. It's 2 plus if we divide, okay, it divided it into 2 bits. We know that 1 is 3 and 1 0 is 2, so 2 plus 3 is 5. For 6, diba 1 is, okay, get it now. 2 per 2 1, it means the weight. Let's get 5 as an example. Decimal 5 is what in BCD 8421? 8421. And what is it in BCD 2421? This 8421 and 2421 represents the weight. The weight of, diba, is 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 3 is 4. No. 1, 2. 2 to the 2 is 4. Then 2 to the 3 is 2 times 2 times 2, which is 8. So 8, 4, 2, 1. 8, 4, 2, 1. But for 2, 4, 2, 1, we will be using 2, 4, and 2, 1 instead of 8, 4, 2, 1. So we will multiply each binary equivalent with 2, 4, 2, 1. For example, let's also write down the binary equivalent. This is 101. Which is the same if we only have one digit. Same with the BCD 8421. If again BCD 8421 is the same as the binary number equivalent, if we only have one digit, we only have 5. But if it's 25 or 15 with an initial digit here, it's not the same. They will not be the same. So 0101. To convert this into BCD, we multiply by 2421. 0 times 2 plus 1 times 4 plus 0 times 2 plus 1 times 1. So we use 2421 instead of 8421. This becomes 4 plus 1, so 5. So that's 5 and 10. 2421. 011. is it? Hmm. We just converted into decimal. This is not the right way. It says here that 24215 is 1011. 1011. Ah, 1011. Anyway, there's a reason why these numbers are chosen this way, but let's not go deeper. This table just shows that for each binary code, we have different binary code representations for the decimal digits 0 to 9, depending on the application. Engineers use different binary codes, and some binary codes have an advantage over the other in the hardware implementation side. So the previous examples, the tables that we showed, BCD, 8421 and 2421 codes are examples of weighted codes. Each bit position is assigned a weighting factor in such a way that each digit can be evaluated by adding the weights of all the ones in the coded combination, as we did earlier. Self-complementing codes. Example 2421 and XS3 codes. The nines complement of the decimal number is obtained directly by changing ones to zeros and zeros to 1. Anyway, let's not go deeper. You can check this for yourselves. Why XS3 code and 2421 are called self-complementing codes. Now we have an example here. Gray code. Continuous or analog information is converted into digital form by means of an analog to digital converter. It is sometimes convenient to use the gray code to represent digital data that have converted from analog to digital. Why? Because only one bit changes its value during any transition between two numbers. For example, 6 to 7, if something changes from, but we know that continuous or analog data, the value changes gradually, so we expect that it does not change abruptly from 3 to 7. It does not happen like that. So gray code is very useful for this analog to digital converters because only one bit changes. For example, 50111 to 60101. Only the second bit changes from 1 to 0. For example, from 11 to 12, 11 to 10. So 1110 changes to 1111. ASCII character code. This is the most used binary code. We're using it in our laptop computers and any other gadgets, because this ASCII code represents the alphanumeric, the alphabets and the numbers. They're represented in binary by this ASCII character code. ASCII stands for American Standard Code for Information Interchange. That's how we pronounce that, ASCII. This is the standard binary code for the alphanumeric characters. See, capital letters are distinct compared to the lowercase letters. For example, if I want to write the ASCII equivalent of my name, for I, ASCII equivalent of, let's follow the bits here. So 7, 6, 5, the 7 bits. The 8 bit is 765 481. 7-bit ASCII code for capital I. This is this row here is for bits 765. These bits here are for bits 4321. So if I can write I, that's 100, 100, and then 1001. For small letter n here, so that's 110, and then 1110. Or if we convert it into BCD, this is 4, and then 9, 49 in BCD. BCD or hex. Since the BCD and the hex are the same, since it does not exceed to 10 to 15, because we know that 10 in decimal is hexadecimal, that's A to F. This, if you convert it into, let's use, let's not use BCD, let's use hexadecimal. So hexadecimal of small letter n, that's 110 is 6, right? 6, and then this one is 6e, base 60, 6e in decimal, hexadecimal, and so on. Let's not go further. So aside from the alphanumeric characters, we also have other control characters used in our keyboards, like for enter, end of transmission or end of text. There's control characters. Yeah. For end of text, ETX. The ASCII code for ETX is 0000011. So ASCII is a 7-bit code, but most computers manipulate an 8-bit quantity as a single unit called a byte. Therefore, ASCII characters most often are stored one per byte. So 1 byte is enough to store one ASCII character. let's take a break. That's it for this video. Our next lesson is in error detecting codes. Thank you for watching, and please subscribe.